Yeah, good evening, everyone. We continue CMOS inverter as an amplifier. Yeah, this is the one we previously talked about. Okay, so yeah, this part. Oops. Yeah, this part is a current amplifier. Say, this circuit works as a current amplifier. Let's see, is it this way or that way? Increases. Looks like the other way around, yeah, this way. So if there is a current, small signal current I flows in, there should be M times I current is sinking at this node. If this node is connected to DC logic threshold voltage, okay? This is also connected to DC level of logic threshold voltage of this inverter, okay? Yeah. So let's see. Yeah, this is only an inverter, right? Yeah, this looks like an inverter and large inverter. And then let's see. Yeah, if this is I1, so there is I1, and then I have a OTA here. Yeah, this should be connected to logic threshold at the DC. So there is some negative feedback of this second amplifier connect this output node at the logic threshold, right? Yeah, if see there is a current I1 flows in there, then this voltage tries to increase, right? Because current flows in, then this OTA reduces this voltage, right? Is it right? True? Let me see. No, increases. Because this rising voltage is connected to positive input node, right? So for this inverter, that inverter input rises, and then this inverter output should go down, right? So because of this negative feedback, there is a virtual ground. This node voltage will be maintained at the logic threshold voltage. However, this voltage will increase, right? This voltage will increase something like so it starts from logic threshold voltage. It increases I1 over GM1. This inverter, the transconductance is GM, right? And then, so if this voltage is increases, then there is current flows out. Is this flows out? Let's just see. This is increases. No, flows in, right? Current flows in. See, gate voltage increases, NMOS current increases, sinking current increases. The sourcing current, PMOS current is reduced, right? So current flows in. This current is just, this is 1, 2M, right? This conductance is MGM. So this is multiplied by MGM. MI1 current flows in, right? So this output voltage, yeah, this flows in. Yeah, this VO is logic threshold voltage plus MN times R, I1, okay? Okay, let's try to simulate this one. So let's see. Yeah, this is a simple inverter. Yeah, this inverter, you can see NMOS is 1 by 1, PMOS is 3 by 1, right? That's sub-circuit inverter. This sub-circuit inverter 10 is multiplied by 10 times. So this inverter 10 is NMOS is 10 by 1. PMOS is 30 by 1, right? So this is 10 times larger. So my small m is 10. And then see, here see, I have a current source here, 0 to 1, 0 to in. Yeah, so I have a current source there. This node is in. This is 0. And then I have an inverter. Input is NX, so output is in. So this is my inverter, okay? And then I have another inverter. This is inverter 10. NX is input, out is, this is my out, okay? And then see what else. Yeah, I have a ideal amplifier. This is a controlling node, right? So it has in is a positive VLT, okay? And I have another E2 which is VO0. So this is connected to VO0. Okay, this is VO. BLT is positive. Out2 is negative. And then I should have a feedback resistor there. This is 20K. So there is a DC 0 volt there, out to I1. So this is for monitoring current, right? Yeah, this VLT is generated by an inverter, something like that, right? By this X3. So this IN is changing from minus 10 microamp to plus 10 microamp, and then try to find this current. IN is closing. Okay. We'll try to find all those voltages. Okay. Yeah, let's just simulate it. What's my spice netlist? I think it is a current amplifier. Okay, do I have that one? Oh yeah, this is it. Is this the one? This is, how come this is AC? Oh yeah, there is a DC. Yeah, this is a DC. Okay. No, grab. So let's see, those voltages, this is current, okay? Let's see, this current works. So this x-axis, horizontal axis is I in. It changes from minus 10 microampere here, 0 plus 10 microampere there, okay? So it should be increased by 10 times, right? Let's see whether it works correctly or not. So this end is, this is only 88 microampere, not 100. There is some offset, right? How about here? Oh, this is around 120 microampere. 0 is around here. Oh, there is a pretty large offset here, right? this zero, somehow there is a large offset. Let's see, how much is the offset here? This is not exactly zero. It's around, let's see, yeah, 1.9 microamp, right? There is a current offset. Okay. Shall we change this one? Or maybe we can add some more. How about the in node voltage? NX node voltage. This is out node voltage. What's out? Out is virtual ground, right? So this VO should be pretty large. VO should be pretty large, okay? Let's look at the VO first. So this is 100K there, right? So looks like it's not symmetric. Y-axis is, yeah, it's not symmetric. Okay, I will eliminate this output voltage. What's this thing for? Oh, yellow one. Oh, this is current. I will eliminate this current. Okay. Then my input voltage is what? Input voltage is red one. So my input voltage is 1.615 around the logic threshold voltage, right? This should be logic threshold voltage. As current increases, it increases slightly. And then NX node voltage. NX node voltage is this magenta one. So NX voltage is changes, but there are some offset, right? At the zero, there are pretty large offset, right? Not we hope it's the same as this logic threshold, but it is not. Okay? And then what's this blue one? Blue one is out node. Out node changes significantly from this logic threshold. There are some offset, right? Pretty large offset. Can we reduce this one by increasing this amp gain? Maybe I will increase this amp gain 10 times. Now let's look at the output node branch. 88, around the same offset, right? Somehow 130 microamp. So there is a unsymmetry, right? So here see, I can see this is 1.6, or this is 1.9 microamp, even larger offset. Okay. Somehow there are some offset. Okay, shall I increase the range like 10 times? I-in range, where is my I-in? Oh yeah, here. 100 microamp to plus 100 microamp. It works pretty fine, okay? How much is the offset here? Oh, this is pretty good. Okay, 1 microamp, 1.083 microamp. This one is around 1 point. How was offset? Offset is, well, offset is pretty, about the same, 1.7 or something like that. So this is looks much smaller, but same offset. We have the same offset. Okay. Question. 네.
이제 그 수동 인버터에서 동작하는 인버터에 커런트가 계속 흐르는 거예요. 그러면 저기 벌써 OPM도 2개가 있는데 다 합하면 파워가 엄청 크지 않나요?
Okay. The question is, Oh, okay. The question is about the power consumption. Okay. So your question is those. Oops. Question is those op-amp will increase power consumption, right?
OPM도 보통 인버터는 한 번 채우고 쉬니까 파워를 트랜지션 할 때만 먹는데 저기는 그 게이트에 물린 게 VLT 주변이어서 인버터에도 계속 전류가 흐르고 있는 거예요.
Yeah. Okay. So your question is at the this works around at the logic threshold. So it will increase the maximum power at the DC operating point, right? That's your question. Yeah. But let's just say, but usually analog circuits flows DC current, right? So yeah, you're right. But if I say for the power consumption, this inverter we can make it small. Even at the logic threshold, we can control the current flowing through it, right? So yeah, this op-amp in analog circuit, it has some current, some DC current, right? So we can control some current here. Yeah, it flows maximum current. It's not like a digital circuit. Okay? So I think the power through this op-amp can be allowed because other parts of the circuit consume comparable power, maybe more than that. Okay? You can control the current through inverters. We can make it small, right? So there are some other advantages. Yeah. Even we can reduce VDD, this supply voltage. Or we can make these devices smaller, not to consume too much power at the logic threshold.
근데 지금 이 인버티드 앰프 사용할 때 그러면 VDD 파워를 만약 줄이면 VDD를 되게 낮게 하면 저기 밑에 있는 그 앰프 사용하는 거는 보통 그냥 이런 디퍼런셜 원스테이지 그걸 사용하게 되면 얘 같은 경우에 저기 게인이 별로 작으니까 플러스랑 마이너스를 완벽하게 딱 같이 그 딱 맞게 이거를 보장을 좀 못하잖아요. 그게 그러면은 그런 거에 대한 문제는 없나요?
Okay. Your question is if we reduce this VDD too much, say close to this VSS, then this op-amp will have some problem. So this will be at the full VDD and VSS. So it has some output voltage range problem. So this is too low, cannot control, right? That's your question. Yeah. One usually we can. Yeah, one other method maybe we can reduce this a little bit. We can increase that part a little bit. So those inverter may operate in around the middle region, around the half of VDD. Yeah, that's one way we can reduce both sides, right? Then see, we need to control this VDD1, this VSS1 together, maybe in a symmetrical way. Yeah, the Chin cell was similar to that. We have a source follow at the VDD and this VSS, right? It reduces the power of inverter symmetrically.